Hello everyone, I want to welcome you to another section. So in this video I'll be talking about another important thing that we have to take note in UV spectroscopy, which is electronic transitions. Electronic transition simply is the position of electron from one orbital to another. Electrons can move from one orbital to another when they probably gain energy. So in UV spectroscopy also, when the molecule in the compound of interest absorb UV light, what happens is that electrons in those molecules move from one orbital to another. And most times the transition of electron occurs between the highest occupied molecular orbital, which we can term as HOMO, to the lowest unoccupied molecular orbital. So this is highest occupied molecular orbital and this is lowest unoccupied molecular orbital. What that implies is that when atoms come together to form molecules, the atomic orbitals of those atoms also combine to form what we call molecular orbitals. And there are different kind of molecular orbitals that we have. We have sigma bonds molecular orbital, we have pi bond molecular orbital. We also have antibody molecular orbitals, both for pi and for sigma. And lastly, we also have non-bonding molecular orbital. That is, these are molecular orbitals that contains non-bonding electrons, probably your lone pair. But like you have said, electron can always move from the highest occupied molecular orbital, whether it is pi, whether it is sigma, or even if it is a non-bonding molecular orbital. So electron move from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. And like I said, transitions of electron occurs when there is absorption of energy. So when UV light or when ultraviolet light or visible light are absorbed by molecules, what happens is that the electron transits from one orbital to another, and then the energy required for transition is also proportional to the wavelength of absorbed light, in the sense that we have already said in videos before this section that energy equals to hc over lambda. This implies that energy is inversely proportional to the wavelength. So what we're trying to say there is that as energy required for electron transition increases, the wavelength decreases. So it also implies that if higher amount of energy is required to cause electron transition from one orbital to another, you need light of lower wavelength. But if less energy is needed for electronic transitions, you need light of higher wavelength. And now I want to talk about the types of electronic transitions that we can have when we have UV absorption. So first, this diagram that we have is the energy profile that shows different kind of transitions in UV spectroscopy. First, like I said, electron can move from different molecular orbitals to another. And I said we have different kind of molecular orbital, starting from the sigma bonding molecular orbital. We have the pi bonding molecular orbital, and we will have non-bonding molecular orbitals. Now, depending on where there are electrons that can transit from one orbital to another, we can have different kind of electronic transitions that can occur when molecules absorb UV light. First, we have sigma to sigma anti-bonding. So when you see this star, it means that we are talking about an anti-bonding molecular orbital. So electrons can move from a sigma bonding molecular orbital to a sigma anti-bonding molecular orbital, and that we can see in this diagram. Now, different molecular orbitals have different energy. So this is the order of their energy. Now, this implies is that the sigma molecular orbital has less energy compared to the other ones, and that is even the reason why the sigma bond is the most stable bonding. So after the sigma molecular orbital, we have the pi. The pi also have a bit higher energy than the sigma, and that means that it is less stable compared to sigma bonds. Now after that is the non-bonding electrons, which is the non-bonding molecular orbital, where you have your lone pairs. So these lone pairs of electrons have higher energy compared to the pi. While pi electrons we have higher energy than electrons in the sigma. But that also in the place of their stability, that means that sigma is the most stable, followed by pi, and the last is the non is the what is the lone pair. Now after the non-bonding molecular orbital, we also have the pi antibonding molecular orbital, and we have the sigma antibonding molecular orbital. So this arrangement is the order of their increasing energy, which also shows the order of their stability. So the one that is below here have the least possible energy and has the highest stability, but the one that have here has the one above, which is the sigma antibody, have the highest potential energy but have the least stability. So but like we are saying that electrons can move from these electrons in the sigma bonding orbital can molecular orbital can move to sigma antibody. So you can see that the gap between the sigma bonding and the sigma antibody is very much. This shows that the energy required for transition of electron from sigma bonding to sigma antibonding is very high, and that implies that light of lower wavelength will require for this transition to occur. So that's the first kind of transition that we can have. And like we have here, we have that the light required for this transition, because we have said it should be a light that has higher energy, which implies a lesser wavelength. The wavelength of light that will cause this transition is about 150 nanometers. In the video before this one, we have mentioned that the ions of the electromagnetic spectrum that we consider in UV spectroscopy is from 200 to 400, which is for the ultraviolet part, and from 400 to 800, which is for the visible part. So but looking at these particular transitions, the wavelength of light required to cause the transition of electron from the sigma to sigma antibonding is around 150 nanometer, which implies that UV light does not have enough energy to cause transition of electron from the sigma bonding to the sigma antibonding, and that implies that this particular transition will be UV inactive. So anytime you have a transition that require a wavelength of light that is below the UV region, that implies that that particular transitions will be UV inactive, which implies that the UV cannot cause that particular transition. So we can say that require is high, wavelength required is low, and 150 nanometer, that is UV inactive. Okay. Yeah, we can. These kind of transitions are actually things that we can see in compounds that actually have single bond, because your single bonds are usually sigma bonds. So compound as alkanes, which have only single bonds, they are UV inactive. Another kind of transition we are looking at, as indicated there, is the what is the N to sigma anti-bonding. So this kind of transition here also requires the energy required for this transition. You can see it from here that the electron move from this non-bonding molecular orbital to the sigma anti-bonding molecular orbital. But the gap between these two molecular orbital is less compared to the gap between this one that we have, which means that lesser energy is required for this transition. So the transition from non-bonding molecular orbital to sigma antibonding molecular orbital requires lesser energy compared to sigma anti-bonding. So you can say that energy required is less than in sigma to sigma antibody. That's star. But at the same time, that means that the wavelength required there, the wavelength required there required is high than in sigma to sigma star, but at the same time it is UV inactive. So even though the energy required in this particular transition is less compared to the one that we need for the sigma to sigma antibody, yet the wavelength of light required here is still not up to 200, which means that the UV light does not have sufficient energy also to cause this particular transition from this part to this particular region. Now the next kind of transition that we have is the next type of transition that we have is this, so which is from this N to pi antibonding. Now, comparing the two, the pi antibonding has lesser energy compared to sigma antibonding, which implies that the energy that we require to cause this transition will be less compared to these first two that we have mentioned. And the energy required is very small, and that's why we have an higher wavelength of about 280 nanometer. So if you look at the wavelength of light required to cause this transition, this is above 200. That means that the UV, as it were, it can cause carries enough energy that can cause this particular transition. So we can say energy required here, energy required is low, wavelength is high, about 280, and then it is UV active. So because the wavelength of light required to cause this transition is above 200, which that implies that we can say that this transition is UV active, in the sense that UV carries enough energy to cause transition of electron from the non-bonding molecular orbital to pi antibonding molecular orbital. Now another one that we also have is the pi to pi antibonding. Pi to pi antibonding. The pi to pi antibonding transition also is shown in this diagram. So, and we can see that the energy required in this case is much more higher than the one that we have in N to pi antibonding, which implies that the energy here, energy in this case, energy required is high than in N to pi antibonding, and then that means that the wavelength is low and is about 190 nanometer, and that means it is UV inactive. So another thing to take note is that the gap that we have between the pi to pi antibonding and the gap that we have between the non-bonding molecular orbital to this sigma antibonding, the gap is somehow similar compared to this one. So that means that these two will require higher energy compared to this one, and that implies that they will require a light of lesser wavelength. And the wavelength of light required to cause those transitions and does not enter into the UV region. That implies that the UV does not have enough energy to cause this transition. And the last one that we have is also the pi to pi star that we have in the conjugated system. Pi to pi star that occurs in a conjugated system is different from the one that we have in an unconjugated system. I believe in the video before this one, I've also tried to explain what conjugated system means, which implies that when you have a single bond between two double bonds. So in a conjugated system, the kind of pi to pi star transition you are going to have is different from the one you will have if there is no conjugation. It's because in a conjugated system, the two double bonds that are separated by a single bond interact in such a way to form, as it were, a molecular orbital, which is what we can show here. So the interaction of these two conjugated double bond, they interact to form two hybrid pi bonding molecular orbital and two hybrid pi antibonding molecular orbital, and that in a way reduces the energy required for electron transition from one orbital to another. So you don't have transition from this normal pi orbital to this normal pi antibody. What you're going to have in the conjugated system will be from this point to this. So the reason why we have this is because of the interaction between the two conjugated double bonds to form as well like an hybrid orbital, which we in a way reduce the energy required for electronic transition. So in a conjugated system, as it were, the energy required for transition of electron is much more lower compared to when you don't have a conjugated system, and that implies that light of higher wavelength will require for this particular transition. So we can say here that energy required is low than in pi to pi star. Wavelength is high and it is UV active. So from all of these things that we have said so far, it implies that sigma to sigma antibonding transition, non-bonding molecular orbital to sigma antibonding transition, and pi to pi antibonding transitions, those transitions are not UV active because the wavelength of light that is required for that transition does not fall into the UV region, which I've said start from 200 to 400. But it is only the N to pi antibonding and pi to pi antibonding of a conjugated system that is only UV active. That was why we started from the point that UV spectroscopy is used in studying systems that have conjugation. It's because conjugation tries to reduce the energy required for electronic transition so in such a way that the wavelength of light that will be required for that transition falls within the UV region. So in summary, I have talked about what is electronic transition. I have also given us different kinds of electronic transitions that we have, and I've tried to indicate the amount of energy required for this transition and which one of the transitions can occur with UV light. So I mentioned that it's only two that UV carries enough energy to cause, which is the N to pi antibonding and the pi to pi antibonding that we have in a conjugated system. Any other transitions apart from these two would be UV inactive because UV does not carry enough energy to cause that particular transition. Now, I'll be mentioning some examples of things that can ask us to do under this aspect that we have talked about. Let's look at some molecules and let's try to determine whether they are UV active or not. Let me start with an alkane. We have, an example is propane, which is CH3, CH2, and we have CH3. So in this molecule that we have here, so the only kind of bonds that we have in the system are sigma bonds. So that means that in this system you can have N to sigma star, you can have N to pi star because the system does not have any atom that carries lone pair of electrons. So all the bonds, all the electrons that we have here, they are sigma electrons. So that means the only kind of transition that we can have here is the sigma to sigma star. So, but from what you have said, sigma to sigma star electronic transition is not UV active. So that means that this molecule itself is UV inactive. So let's look at another example. Let's talk about diethyl. They give us something like diethyl ether. So we're going to have CH3, CH, we have O, double bond, we have CH2, we have CH, and we have H. Now in this molecule, they can also ask what are the kind of electronic transitions that can occur in this phase. First, we can have, because we all have sigma bonds in the system, so we can also have sigma to sigma antibody transition, but that transition is UV inactive. Because of the lone pairs of electrons on oxygen, we can also have N to sigma antibody. But like I have said, that N to sigma antibody also is UV inactive. That means that this entire molecule also is UV inactive because the energy carried by the UV light is not capable of causing any electronic transition in this system. Another example is, let's talk about propene. Propene is C, we have H2, double bond, CH, and we have CH, and we have CH, and we have H. Now in this system now, we have sigma bonds and we also have a pi bond, because this is in a double bond you have a pi and a sigma. So in this system now, we have many sigma bonds and just one pi. So that means in this case, we can say that the electron transition that can occur there includes the following. We can have sigma to sigma star to sigma antibonding. We can also have pi to pi antibody. I think those are the major two that we have. But we can't have the last type of transition because that one has to do with conjugation. And in this system, there is no conjugation. So these two electron transitions that we have in this compound are also UV inactive. So that means that the molecule itself, the compound itself also will be UV inactive. So let's look at another example. Let's talk about probably propanone. Propanone is CH, we have H, we have H, we have C double bond O, we have CH, we have H, we have H. So in this molecule also, we have, don't forget, oxygen here carries two lone pairs. So in this system now, we can have different transitions. We have sigma bonds in the molecule, we have pi electrons in the molecule because there's a double bond between oxygen and carbon, and also have lone pairs of electron on oxygen. So that means that to highlight the electron transition that can occur in this molecule, we can also have sigma to sigma antibonding. We can have N to sigma antibonding. We can have N to pi antibonding, and we can also have pi to pi antibonding. So these are the four electron transitions that we can have in this system. But out of all of them, only one of the transition is UV active, which is the N to pi antibonding. So that means that this molecule that we have here will be partially UV active, but the intensity of the absorption might be very low. So because of this N to pi antibonding transition that can occur in this molecule, that makes this molecule to be able to absorb light in the UV region. Let's look at this compound. Let's look at this compound. We have this, we have this, we have this, we have this, and we have this. This is good. We have 1, 3, we have 1, 3 diene. Now in this molecule, in this particular compound now, in this compound that we have, the double bond, the two double bonds that we have in the system are separated by a single bond. So if they ask that what kind of transitions are we going to have in this molecule, so we have the first one, we can have the second, we can have this one, we can have this one, because there is no lone pair of electron in the system, and we can also have this. But at the same time, because already I've said the double bond in this system in this molecule already are conjugated, that means this kind of of transition that we're going to have there, and that means that the molecule itself will be UV active. And one thing that we must also take note before I round up is that the higher the conjugation, the lesser the energy and the higher the wavelength. And these are some of the things that they can ask us to do. They can give us different molecules and they will ask us to align different electronic transitions that can occur in the molecule, and at the same time determines if the molecule at the end of the day will either be UV active or not. So at this point, I'll be rounding up, and I believe in subsequent videos we'll still talk more and look at further examples that can also help us to understand better. So I believe that you have learned one or two things in this video. If you have any question, any confusion, you can try to drop your question in the comment section. I will do well to respond to your questions. So I do hope that you watch, you share with friends that can also be in the beginning of this video, and please do well to subscribe and to share. Thank you.